What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 9, Review Exercises. Let's do it. So for question number 1, we're solving for t, and I'm going to rewrite it as x, but it's still the same thing, just an unknown variable. So we got cosecant squared x equal to 3. My first move is I'm going to take the square root of both sides like so, and then I get cosecant of x equals rad 3. Now, for cosecant, it's important to remember that it's the same as 1 over sine of x. It's the reciprocal, right? So we got 1 over sine of x equals rad 3. And then if I multiply the sine across while simultaneously dividing by rad 3, we now have sine of x equal to 1 over rad 3. You don't have to do this, but this is just, to show you, right? Sine relates to the y values on the unit circle. Cosecant relates to the reciprocal of the y values, but this might be a little bit easier. And then I want to rationalize my denominator, right? So I'm going to multiply by rad 3 over rad 3, and we get sine of x equals rad 3 over 3. Okay, now we'd want to use the unit circle and see, hey, does this exist for any of the y values on the unit circle? Unfortunately, rad 3 over 3 does not. So what we then do to find the exact solutions is we take arcsine, okay? So we take arcsine of this value, and this is going to give us an angle. So this is going to give us one angle. Now, since this is a nice positive value, for arcsine, this is going to output in the first quadrant, okay? But the thing is that sine actually returns positive values in the first quadrant and the second quadrant. So we need another angle that will also give us the same answer, right? And that other angle is, like I said, that same reference angle, but in the second quadrant, which can be found by taking this angle in the first quadrant and subtracting it from pi. So my second answer is this amount subtracted by pi, or subtracted from pi. So pi minus arcsine of rad 3 over 3. So these are your two answers. Boom, done. For this one, I'm going to start by dividing both sides by 2. So I have sine of, and instead of theta, I'm going to write it as x, but it's the same thing. So sine of x equals negative 1/2. Now this is beautiful because all I need to do now, if this value exists on the unit circle, is find where it exists for the y coordinates, because sine connects to y, and we do have it occurring right here and as well right here, right? So that means our two values for x, which is actually theta, are going to equal the corresponding angles, 7 pi 6 and 11 pi 6, okay? 7 pi 6, 11 pi 6, that's how you do it. Boom, done. For this one, I'm going to start by setting everything equal to 0. So I'm going to subtract 9 sine w and add 2. And I'm going to replace the w with x just because it's easier to write. Boom, there we go. Then what I'm going to do is I'm going to do a little substitution. This is optional, but I'm going to set y equal to sine of x. Just going to be easier for us to see whether or not this is factorable. So this is 4y squared minus 9y, right? Sine of x becomes y plus 2. Now the question is this factorable? So I'm going to use a little star method because we have a leading coefficient of 4. So I'm going to put a, b, and c. A goes up here and here. A times c, 4 times 2 goes up here as 8, and negative 9 goes down here. Now the question is, are there any two numbers that multiply to positive 8 and that add to negative 9? Yes, negative 1 and negative 8. Beautiful. So it is factorable. Simplify this side like a fraction. You simplify both sides like a fraction. It's just this is fully simplified. Divide both by 4, we get 1 and negative 2. And the top number now goes with the variable in front, like the 4 and that 1. And then the bottom number goes as a standalone constant here and here, minus 1 and minus 2. Now, I could put y in, but why not jump ahead and just plug sine of x back in? So we got sine of x, beautiful, beautiful. And this is all equaling 0, right? So what we really have now is two equations. We have the first equation when this amount, this quantity, 4 sine of x minus 1 equals 0. And we also have this when 1 sine of x minus 2, or just sine of x minus 2, equals 0. So now I'm going to solve both of these. I'm going to add 1. We got 1 equals 4 sine of x. Then we divide by 4. Sine of x equals 1/4. So this is 1. The other one will add 2. And we have when does sine of x equal 2? Now, this is interesting because sine of x can only output values for its range between negative 1 and 1. We're trying to get it to equal 2. That's not possible. So this is a no solution situation. This one, however, is doable. 1/4 is not on the unit circle. So what I have to do is take arcsine of both sides and say that the answer is arc sine of 1/4. Now, if you remember, arc sine will output values in this range, right? Between negative pi halves and pi halves. So arc sine of a positive is going to give me something in the first quadrant. But we can also get another answer in the second quadrant. Why is that? Because sine outputs values that are positive in the first and second quadrant. So we need another angle in the second quadrant that has the same reference angle as this, which can be found by just subtracting it from pi. So pi minus arc sine of 1/4. And these are the two solutions. I'll just put a little comma there. These are the two solutions. That's how you do it. Done. So for this one, to simplify, we're going to leverage the fact that secant of x is equal to the reciprocal of cosine, 1 over cosine x, right? So I'm going to replace secant with that now. And you notice that 1 over secant of x becomes cosine of x, just like 1 over cosine would be secant. So cosine minus cosine, that's 0. 1 over cosine times cosine, those cancel out. That's just 1. So we're left with 1. Boom, done. So for this one on the left-hand side, what I'm going to try and do is I'm going to try and get a common denominator of cosine squared, because that's what we have on the right side. So let's start with that. So I'm going to take my sine squared and I'm going to multiply it by cosine squared x over cosine squared x. I'm allowed to do that because cosine over cosine is 1. So I can multiply anything by 1 and it won't change. For secant, that really is 1 over cosine squared x, because secant is the reciprocal of cosine. And then for the 1, I'm going to multiply that again by cosine over cosine. Now what I'm going to do is I'm going to merge everything together. But before I do that, what I'm going to take this sine squared here. And we don't have a sine squared on the right-hand side. But because of our Pythagorean identity such that sine squared plus cosine squared equals 1, I can replace sine squared with 1 minus cosine squared, right? Because if I subtract cosine squared from both sides from this, I get sine squared equals 1 minus cosine squared. So I'm going to plug this in for sine. And then I'm going to rewrite everything else as it was. We got the cosine, we got cosine squared for the denominator. And then since everything has a denominator of cosine squared, I can just merge it onto one numerator, plus 1 and then minus cosine squared out here. Now what we're going to do is we're going to distribute, and we got cosine squared x minus cosine to the 4th x. And then we've got plus 1 minus cosine squared x. That's the numerator. Now these guys are going to cancel out like so. And now we're left with 1 minus cosine to the 4th of x, right? I just flip-flop these. This is negative, so I put it here, and then the 1's positive. Okay, and I have all of this over cosine squared. Last thing, this is a difference of squares, and it can be factored into 1 minus the square root of that, which is cosine squared x, times 1 plus cosine squared x, right? And all of this over cosine squared x. Guess what? That's what's here on the right-hand side. So we verified the identity, boom, done. So for this one, we're going to use the angle sum or difference identities because 7 pi 12ths is not an angle on here. But we can rewrite 7 pi 12ths as the sum of 3 pi 12ths and 4 pi 12ths using the angle sum identity. So why is this better? Because 3 pi 12ths is really pi 4ths and 4 pi 12ths is really pi 3rds. And that's great because we have pi 4ths and pi 3rds on the unit circle. Okay, so now let's use the formula because I can reformat as tangent of x plus y as this. So let's do that with these values now. So on top we have tangent of pi 4ths plus tangent of pi 3rds over 1 minus tangent pi 4ths times tangent pi 3rds. Okay, now we have to figure out what these values are. So tangent pi 4ths is the y over the x of that coordinate. Well, since they're the same, that's 1. And then tangent of pi 3rds is again y over x. So rad 3 over 2 divided by 1/2 is just rad 3. And then over 1 minus, again, that's 1. So I don't even have to write that. And then tangent of pi 3rds, as we already mentioned, is rad 3. So this is pretty much good to go. However, in the answer, they've rationalized that denominator by multiplying by the conjugate of 1 minus rad 3 to get the radical out of the denominator. So how do we get a conjugate? We take this and we multiply by the same thing, 1 and rad 3, but we flip the sign. So if it was a plus, it'd be a negative, but since it's a minus, we make it a positive. Now we're going to FOIL the top. So on top, we get 1 rad 3, which is 2 rad 3. And then rad 3 times itself is just 3. And then over on the bottom, we get 1. And then we get rad 3 and negative rad 3, which cancel out. And then we get negative rad 3 times rad 3, which is negative 3, okay? So now let's combine like terms on the top and the bottom. And we get 4 plus 2 rad 3 over 2, or sorry, negative 2, excuse me. Divide both by negative 2, we get negative 2 minus rad 3. And that's how you do it. Done. So for this one, we're going to use the sum and difference identities, but we're going to do it in reverse, okay? So you can see that we have sine, cosine, cosine, sine. That looks pretty similar to this identity, right? Sine, cosine, cosine, sine, and those angles are consistent. So we can rewind this to be sine times the difference of 70 and 25. So what is this? This is really sine of 45. 45 is on the unit circle right here. So sine corresponds to the y values. So that's the y value at 45. So the answer is rad 2 over 2. Boom, done. So for this one, we're going to start by using the angle sum identities, okay? And in particular, we're going to use the cosine sum. So cosine of 4x is really cosine of 2x plus 2x, and then cosine of 3x is really cosine of x plus 2x. And then we still have that cosine of x there, so now we're going to use this identity to expand this out. So as you can see here, it starts by cosine of x, cosine of y, so both the x and y are the same, so we got cosine 2x, cosine 2x, minus sine 2x, sine 2x, right? And then minus cosine x, cosine 2x, minus sine x, sine 2x with that cosine still at the outside. Now using my double angle identity for cosine 2x times cosine 2x, right? Cosine 2x right here can be rewritten as cosine squared x minus sine squared x. So this is cosine squared x minus sine squared x squared. So this piece is now rewritten as this. And then again, using a different double angle identity, sine of 2x is this. So it's this times itself, which is this squared, which is minus 4 sine squared cosine squared. And then for all this stuff, I'm going to distribute the negative and distribute the cosine squared. So then we have minus cosine squared x cosine 2x. And then the negatives are going to cancel out, plus sine x sine 2x, and then cosine of x. Now what I'm going to do is I'm going to FOIL this first thing out, which becomes cosine to the fourth x minus 2 sine squared x cosine squared x plus sine to the fourth x, and then this leave it as is. And then for this double angle here, I'm going to use the top identity. And then for this sine of 2x, I'm using obviously only that identity. So then we have plus, and then we get 2 sine of x times sine of x here gives me sine squared x. And then, of course, the cosine here multiplies this cosine, and we get another cosine squared x. Now we need a lot more room, so I'm going to remove all this stuff and write it out simplified. Hopefully we got enough room left. So then all of this top row is pretty chill. It's the bottom that needs to be simplified. So as we distribute the cosine squared, we get minus cosine to the fourth x, and then plus sine squared x cosine squared x, and then this is just chilling. Now the fun part, now we're going to combine like terms, and since this is just such a crazy identity, I'm going to kind of color coordinate. So we got cosine to the fourth x minus cosine to the fourth x, those cancel out. So what I'm going to do now is I'm going to group this and this together, and then this, and this are going to combine to just have negative 4 sine squared cosine squared. Now for these two, I'm going to do a little factoring, right? I can factor out a sine squared from both of them. So pulling out a sine squared x, I've got another sine squared x, and then just a cosine squared left like so, and then minus 4 sine squared cosine squared. Now the beauty of all of this, sine squared plus cosine squared is 1. That cancels out. And then we're left, finally, this one's a doozy, sine squared x minus 4 sine squared x cosine squared x. Man, oh man. So that is how you do it. Identity verified, done. So for this one, we're meant to simplify, and I've got the sum difference identities up here because you might notice that this certainly looks like this, where my x and y seem to be 1/2 x and 1/8 x, right? And so knowing that, I can kind of rewind this into tangent of 1/2 x plus 1/8 x. And by the way, you know, to get common denominators, 1/2 can be 4/8. So 4/8 x plus 1/8 x is 5/8 x. And that's how you do it, done. So for this one, I could use the angle sum identity for tangent, but instead I can evaluate what arc sine of 0 is, because arc sine of 0 is really saying for what radian value am I getting an output of 0, meaning a 0 y coordinate. And that's pretty much happening here at 0 and pi. So this is going to actually evaluate to just 0 radians. And then arc sine of 1/2, that's occurring right here when we have a y value of 1/2, which means that is like pi6, okay? So really what we're talking about is we're taking tangent of this, tangent of 0 plus pi6, which is really tangent of pi6. And tangent of pi6 can be found by finding pi6 and then taking the y over the x. That's what tangent is, right? Sine over cosine, or y over x. So it's 1/2 over rad 3 over 2, which is the same as 1/2 times the reciprocal of this, which is 2 over rad 3, cancel, and we get 1 over rad 3. Last but not least, let's rationalize the denominator like so, and then we get rad 3 over 3, boom, done. So for this one, we're meant to find this, this, and this, given that secant of theta equals -5/3. So the first thing I'm going to do is I'm going to draw out a triangle, and I'm going to recognize that secant is related to cosine, right? And cosine is the same as adjacent over hypotenuse, right? Well, if secant is the reciprocal, it's hypotenuse over adjacent, which means that hypotenuse over adjacent, so my hypotenuse is 5, the adjacent side is 3. Now, you may not recognize this triangle, but it's a 3, 4, 5 triangle. This is just not drawn to scale, just bear that in mind, but this is a great setup. Now, what you might say, what about the negative? I'm not going to worry about the negative, because this is telling me that if I'm between pi halves and pi, I'm in the second quadrant. So I already know the signs of sine, cosine, and tangent in the second quadrant, okay? But we're going to come back to that. Now, to make this easier, okay, I'm going to tell you what sine, cosine, and tangent of theta are. I'm going to write them out, okay? So since sine of theta is opposite over hypotenuse, it's 4/5. Cosine is adjacent over hypotenuse, which is 3/5. And tangent is opposite over adjacent, which is 4/3. Now, sine of double theta is 2 sine cosine, so it's 2 sine theta, which is 4/5. And then cosine theta, which is 3/5, which equals 24 over 25. Now, again, that is sine of 2 theta. We still haven't addressed whether or not this is positive or negative. We'll get back to that. And then cosine of 2 theta, let's use this one, cosine squared minus sine squared. So cosine squared would be this squared, which is 9 over 25, minus sine squared, which is this squared, which is 16 over 25. So when we subtract those two, we get -7 over 25. And then last but not least, we have tangent of 2 theta. So that's 2 times tangent of theta. So 2 times this is 8/3 over 1 minus tangent squared. So that's this squared, which is 16/9. Now, 1 minus 16/9 is really 9/9 minus 16/9, which is -7/9. And then this would simplify by taking this times the reciprocal of this. So 8 over 3 times 9 over 7. Negative 3's cancel out. That's 1 and 3. And then we get -24 over 7. So now we get to the question of the sign of these, right? So what is theta? Like, we don't exactly know, but I can tell you since the opposite angle is 4, okay? If we think about a reference angle, if we were to, draw this out in the unit circle, I know it's a small one, but that reference angle, okay, is this angle in here. It's obviously bigger than 45 degrees, okay? What that means is we're talking about then an angle that must be less than 135. Let's say 130, for example, okay? If you double 130, you get 260. That lands us in the third quadrant. That means, therefore, in the third quadrant, sine is negative, cosine is also negative, but tangent is positive in the third quadrant. Again, that's for 2 theta. So these are your final answers. That's how you do it. Done. All right, so for this one, we're going to start by recognizing that secant is the same as 1 over cosine of 3 pi 8ths, right? The reciprocal identities. And then the situation is that 3 pi 8ths is not on the unit circle. So I'm going to use this identity because this is the same as cosine of 3 pi 4ths over 2, right? And this is nice because we know what cosine of 3 pi fourths is. It's on the unit circle. It's negative rad 2 over 2. So then this becomes square root of 1 minus rad 2 over 2 because it's negative, right? Over 2. And again, this is on the denominator of 1. So now what I'm going to do to simplify is I'm going to multiply by the conjugate of this inside piece, okay? And what that's going to do is it's going to be radical of 1 plus rad 2 over 2 over 2, right? Just changing the minus to a plus. And of course, I have to have this in the numerator as well, like so. So now we multiply across. We're going to go above here, then we're going to come down at the end. We've got radical of 1 plus rad 2 over 2 over 2 over, and then now's the interesting part, right? When we multiply these together, underneath the radical, we got 1 times 1, which is 1. And then we've got 1 times rad 2 over 2, 1 times negative rad 2 over 2. Those are going to add together and cancel out. Then I got negative rad 2 over 2 times rad 2 over 2, which is negative. Rad 2 times itself is 2. 2 times 2 on the denominator is 4. And then over 2 times 2 on the denominator, which is 4. Okay, now let's bring all this down here, and we still got some simplification to do to get to the answer that they have in the back of the book. So we're going to leave the top as is right now, and then the denominator becomes 1 minus 1/2, which is 1/2 over 4. And 1/2 divided by 4, by the way, is 1/8. So now I got this whole nice situation. And by the way, if it's a radical over a radical, now I can merge it to be one big radical. And really what we're doing now is we're dividing this by this, which is actually multiplying by the reciprocal of that, which is just 8. So now I have 8 times 1 plus rad 2 over 2 divided by 2 like so. That cancels out and becomes a 1 and a 4. So look at that denominator's gone. And now we have radical 4 times 1 plus rad 2 over 2. Now, the only thing they did that's different in the answers is they've taken a 2, like imagine 4 is 2 times 2. They take one of the 2's and they distribute it here and here, leaving a single 2 on the outside. They get 2 plus rad 2 like so. That's how you do it. Done. So for number 25, we're going to use our half angle identity. So I got them listed up here. So first we're going to do b over 2, and there's b, or beta. So it is the square root. And by the way, these are all first quadrants, right? So when you're looking at the plus or minus, all of these are going to come back positive. So you have the square root of 1 minus cosine of b, right? And cosine of b is adjacent over hypotenuse, which is 24 over 25. And then all of this is over 2. So if we're to simplify this, 1 minus 24 over 25 is 1 over 25. And then that divided by 2. 1 over 25 divided by 2 is the same as multiplying by 1/2. So it's really 1 over 50. Now to rationalize the denominator, multiply by rad 50 over rad 50. And I get literally rad 50 over rad 50 times rad 50 is 50. Now if we're to simplify this a little bit using our radical rules, we know that 50 is really 2 times 25. So the 25, you can take the square root of that. That comes out as a 5. So you're left with 5 rad 2 over 50, which then simplifies to divide by 5 on top and bottom, and we get rad 2 over 10. So that's the first answer. Now for cosine of b over 2, it's the same identity, except instead of minusing like they have in sine, it's plus here, right? So we can kind of shortcut this and say instead of 1 minus 24 over 25, it's 1 plus that, which would give us 49 over 25, right? Because 1 becomes 25 over 25, and then it's a plus instead of a minus. And then again, it's all over 2, which means we're left with radical of 49 over 50. All right, so this is pretty interesting because radical of 49 is just 7. And then as we mentioned here, 50 is really 2 times 25, which allows us to take the square root of the 25, which is 5, leaving a radical 2 on the inside. Last but not least, we want to rationalize the denominator, so we multiply by rad 2 over rad 2, and we get 7 rad 2 over rad 2 times rad 2 is 2 times 5 is 10. Okay, there's our second answer. And then let me box these. And then we come to tangent of b over 2. So the half angle identity there is sine over 1 plus cosine of x. Okay, or that one, but we'll use the first one. Now the problem with sine, okay, is we don't know this side, but using Pythagorean's theorem, we can find it. And it's leg is 24, leg is 25, and then solve for that. Well, the nice thing is this is a Pythagorean triple. If you recognize that, it's a 7, 24, 25. But if you don't, use Pythagorean's theorem, x squared plus 24 squared equals 25 squared. Okay, So now we have sine of x, or beta, which is opposite over hypotenuse. So on top we have 7 over 25. And then on the bottom, we have 1 plus cosine of x. We already figured out that cosine of x is 24 over 25, right? And we already know that 1 plus that was 49 over 25. So we have 49 over 25 in the denominator. And the cool thing is when they both have the same denominators, we can kind of cancel them out. So we have 7 over 49, which simplifies to 1 over 7. Now we come to this, this, and this. So let's go through that same process. Sine of a over 2, again, using that half angle identity. So it's 1 minus cosine of a. Cosine of a is adjacent over hypotenuse, which is 7 over 25 divided by 2. And again, 1 can be rewritten as 25 over 25. So 25 minus 7 is really 18 over 25, and then we still got over 2. And then dividing by 2 is like multiplying this by 1/2, so it is radical 9 over 25. And those are both nice perfect squares, so we get 3/5. Nice, boom. Now for this one, it's going to be the same thing we have here. We just replace that minus with a plus, right? And then 25 over 25 plus 7 gives us a nice 32 over 25 divided by 2. And then that's like multiplying by 1/2, and we really take half of 32, which is 16 over 25. And those are nice perfect squares, and that becomes 4/5. Last but not least, we got the tangent. So we're going to use that first identity, which is the sine of x, or sine of a. Sine of a is opposite over hypotenuse, so it's 24 over 25 on top, over 1 plus cosine, and we already know that cosine is adjacent over hypotenuse, 7 over 25. So 1 can be 25 over 25, so 25 plus 7 is 32. So we got 24 over 25 over 32 over 25. Same denominators, 25 and 25 can be canceled out. We got 24 over 32, divide them both by 8, and we get 3 over 4. So that's a doozy, but that's how you do it. Done. So for this one, we're trying to prove this identity. The first thing I'm going to do is I'm going to use a double angle identity for cosine of 2x. And then what I'm going to use is this top identity here. So, and by the way, cotangent, I'm going to rewrite that as cosine of x over sine of x. So then we're multiplying by cosine squared x minus sine squared x. This is, of course, over 1. I just put it like that. So, you might be like, hey, how do we do this? Now we're going to distribute. And we've got cosine cubed x minus cosine x sine squared x all over sine of x. Now I'm going to separate these out into 2 different fractions by splitting it up. So I got the first term, cosine cubed x over sine of x, and then minus cosine x sine squared x over sine of x. So this is going to cancel out with this. So this one on the right, we got minus cosine of x sine of x. And then over here, I'm gonna rewrite this as cosine x times cosine squared of x over sine of x. So why am I doing this? Because these two are going to turn back into cotangent, and that's going to be great. So now I got cotangent of x times cosine squared of x minus cosine x sine of x. Then what I'm going to do using a Pythagorean identity, which says that cosine squared x equals 1 minus sine squared x. I'm going to plug this in for the cosine squared x. So now as I distribute, I got cotangent x minus cotangent sine squared x, right? And then minus cosine x sine of x. Now this cotangent of x is golden because I need that here, right? And then what I'm going to do, this one I don't want because really we're only having one instance of cotangent of x. So that's an indication that I should turn it back into cosine over sine. And then it's still times a sine squared x, right? And then we got that minus cosine of x sine of x. So that's pretty cool. Now this cancels out with this, and then we have cotangent of x minus cosine of x sine of x, cosine of x sine of x, which becomes 2 cosine of x sine of x. Now, if you remember, this is our double angle identity for sine of 2x, which means now we're back to cotangent of x minus sine of 2x. And that's basically this. They just flipped it around. That's how you verify the identity. Done. So for this one, I'm going to start by using a Pythagorean identity to simplify. And I just want to give a caveat right at the beginning that the answer I'm going to provide is going to be it's going to meet the criteria that it's asking, but it's going to be different than what's in the back of the book. So let's proceed according to that. So first of all, I see that tangent squared plus 1 is secant squared, which means I can replace tangent squared with secant squared x minus 1. And then with the sine cubed, I'm going to rewrite that as sine squared x and sine of x. The reason why I'm doing this is because I can also use this identity to rewrite sine squared x as 1 minus cosine squared. Now that we have this, we can do a little bit of foiling. We go boom, 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 boom. And then first we get secant squared x. Then secant squared times cosine squared x is, they're inverse functions. They're reciprocal functions, which means that just becomes -1. Then -1 times 1 is again -1. Then -1 times negative cosine squared is positive cosine squared. So now we're going to combine like terms, and we got secant squared x minus 2 plus cosine squared x all times sine of x. All right. Now as we distribute the sign, boom, boom, and boom, secant times sine. Remember that a single secant times sine gives us a tangent of x, because secant is 1 over cosine. So sine times 1 over cosine, it's sine over cosine, which is tangent. And then we have 1 secant left over. So you see, we already meet that criteria. That's a single power, that's a single power. And then minus 2 sine of x, right? And then plus sine of x cosine squared of x. Now we have an exponent of 2. We got to get rid of that. So I'm going to use my half angle identities, which is, this is the same thing as cosine of 2x over 2. And then that whole thing squared. And just so we can see the identity, it becomes the square root of 1 plus cosine of 2x over 2. But because the whole thing is squared, it's squared, which basically just gets rid of the radical. So basically now we have all of this, and then I'm replacing cosine squared x with, 1 plus cosine of 2x over 2. And there we go. Everything has been reduced to a power of 1. Boom, done. So for this one, I'm actually going to use the product to sum, because I recognize it's sine times sine, right? Which occurs right here. And that means that A is 2 pi thirds and B is 5 pi 6. So then to substitute in, it becomes 2 times, and then we have 1/2 of cosine of the difference of these two. And by the way, 2 pi thirds is the same as 4 pi 6, right? So the difference of these two, 4 pi 6 minus 5 pi 6 is negative pi 6. And then we have minus, and I added in a parentheses there just to make sure everything's multiplied by 1/2, minus the sum of these two, 4 pi 6 plus 5 pi 6, which is 9 pi 6, which reduces to 3 pi over 2. And of course, the 2 and the 1/2 cancel out. Now we'll use the unit circle to get these values. So cosine of negative pi 6, that's going backwards. So it's basically the same as 11 pi 6. So cosine of 11 pi 6 is the x value, which is rad 3 over 2, minus cosine of 3 pi halves. Here's 3 pi halves. Cosine is, again, the corresponding x value, which is 0, which means we simply have a final answer of rad 3 over 2. Boom, done. So for this one, we're going to go sum to product, and I got sine minus sine, so that's right here. So I'm going to set A equal to that first angle and B equal to the second one. Now using the formula, I have 2 sine of A minus B divided by 2. So A minus B is negative 6 pi 12ths divided by 2 is negative 3 pi 12ths, right? I'm taking half, and that simplifies to negative pi 4ths, which is on the unit circle. And then for A plus B, we get 8 pi 12ths, but then again, divided by 2 is 4 pi 12ths, which simplifies to pi thirds. Now we're going to use the unit circle. So sine of negative pi 4ths, that's really right here. Same as 7 pi 4ths, which is that corresponding y value, which is negative rad 2 over 2. And then cosine of pi thirds is occurring here. Cosine is that corresponding x value, which is 1/2. Boom. This cancels out with this, so we're left with negative rad 2 over 2. Boom, done. So for this one, we want to change it from a product to a sum. So we're going to use these down here. And in particular, it's sine, cosine. So I'm going to use this top one right here. So we're going to set A equal to 9x and B equal to 3x. So we got 1/2 times sine of A plus B, which is 12x, and then plus the difference, sine of 9 minus 3, which is 6x. And that's how you do it. They flipped it in the answers, but it's the same thing. Boom, done. So for this one, we got sum to product. We got sine plus sine, which is this guy right here. So I'm going to set a equal to 11x and b equal to 2x. And then we've got 2 sine, basically the average of these two. 11 plus 2 divided by 2, which is 13x over 2. And then times cosine of the difference of those two divided by 2. 11 minus 2 is 9x divided by 2. That's how you do it. Done. So here we're solving for this equation, finding all solutions from 0 to 2 pi. So what I'm going to do is I'm going to subtract 1 from both sides to start. Now what this is saying is, when is tangent of x equal to -1? And tangent occurs on the unit circle when you have y divided by x. So when is y divided by x equal to -1? Well, it's when they're the same, but they have different signs. So I see that here and I see that here, right? So that means my two solutions in this from 0 to 2 pi is going to be 3 pi fourths and 7 pi fourths. So we say 3 pi fourths, 7 pi fourths. That's how you do it. Done. So for this one, let's start by factoring out sine of x. And then I got sine times 2 sine of x minus 1. And they're both equal to 0, this and this. So that means we can make two separate equations when this goes to 0 and then also when the second one goes to 0. Okay, now let's solve. So when is sine of x going to equal 0? AKA, when are we getting a y value of 0 on the unit circle? Here and here. So this one gives me two values of 0 and pi radians. And then for this one, we're going to add 1, divide by 2. When does sine of x equal 1/2? Okay, so again, sine is the y value, so I see a positive 1/2 occurring here, and I also see it here. So that's going to give me pi 6 and 5 pi 6. So those are the 4 solutions. Done. For this one, I'm going to start by setting sine of x equal to y. Now this is an optional step, but the reason why I like to do this is because I feel like it makes it easier to see if this is indeed factorable, right? Because now we got A, B, and C. So using the star method, we can check where I have A here and here, A times C, 2 times 3, 6 here, and then B, 5 here. And then we ask the question, are any two numbers able to multiply to that and add to that? Yes, we have 2 and 3, so it is factorable. Now this simplifies like a fraction. We get 1 over 1, and then that doesn't, so we got 2 and 3. So now we have y plus 1. The top one goes with the variable, bottom standalone constant. And here we have 2y plus 3. Now let's substitute sine of x back in. And now we get two equations from this. First, sine of x plus 1 equals 0, and then this. So sine of x plus 1 equals 0 is the same as sine of x equals -1. For this one, when it equals to 0, we would subtract 3, divide by 2. So it's saying, when does sine of x equal -3/2? So this is interesting because this is outside of the range of sine. We can only get values between -1 and 1. So this is a no solution. But what about this one? This is really asking, when on the unit circle does the y value equal -1? And that's only in one spot here, which means my answer is 3 pi over 2. That's how you do it. Done. So for this one, it's important to note that 1 over secant squared is the same as cosine squared x, which means I can now merge these together and make that 5 cosine squared x. And then I have this sine squared x. I don't like that because I got cosine and then I got sine. So I got two different things going on. So instead, I'm going to change sine squared x to 1 minus cosine squared. So where do I get that? Because sine squared plus cosine squared equals 1. So if I subtract by cosine squared on both sides, I get sine squared x equals 1 minus cosine squared x, okay? So then I have plus 2 plus 1 minus cosine squared x, and then these can combine, then I get 4 cosine squared x plus 3, and again, this all equals 0. Okay, now this is much nicer situation. Now I can subtract by 3 and divide by 4, so I get cosine squared x equals -3/4. But this is a problem, because we're expecting something to be squared to be negative. That's not a thing with real numbers, which means this is a no solution situation. Done. So for this one, we're going to factor. And first what I'm going to do is I'm going to set y equal to cosecant of x. So we can see the factoring possibilities a little bit easier. So it's y squared minus 3y minus 4. And then the question is, are there any two numbers that multiply to this and add to this? And there are. It's y minus 4 times y plus 1, right? -4 times 1 is -4. -4 plus 1 is -3. Now I'm going to put the cosecant back in, and we have all this equal to 0. So this gives me two possibilities. One, cosecant of x minus 4 equals 0. The other one is cosecant of x plus 1 equal to 0. So when we isolate, we take cosecant of x equal to 4 and cosecant of x equal to negative 1. Now, if your calculator doesn't allow you to take arc cosecant of both sides, you might want to switch it to 1 over sine of x equals 4, 1 over sine of x equals negative 1, and take it from there. But I'm going to use Desmos, and we can take arc cosecant of both 4 and negative 1. So let's do that now. So for arc cosecant of negative 1, we get this value. But look, it's negative, and I don't want a negative value. I need this to be between 0 and 2 pi. So I'm going to find a coterminal angle to this by adding 2 pi. And now we get our nice value of 4.7124. And in case you're not sure what this is 3 pi halves, okay? And the thing is, we're not going to get another angle, right, that is going to give us this same value, because usually, let's say we have a value giving us, something in the second quadrant, or let's say third quadrant, right? Third quadrant, cosecant and sine are negative. So you should also have a second solution in the fourth quadrant where sine is also negative and cosecant is also negative. But this is actually on the y-axis. So this is 1 of 1. Now, arc cosecant of 4 gives us 0.2527. But remember, this angle, this is less than pi halves. So I know this is in the first quadrant. And cosecant is positive in the first quadrant, but it's also positive in the second quadrant. So to get that same reference angle in the second quadrant, I subtract this from pi. And we also get this value. So rounded to 4 decimal places, these are the 3 answers. Done. So for this one, we're going to start by setting everything equal to 0 by subtracting both sides by 15. Then we're going to see if this is factorable, right? So are there any two numbers that multiply to this and add to this? And there are. It's negative 5 and positive 3. So now I got two equations. I got secant of x minus 5 needs to equal 0, and secant of x plus 3 needs to equal 0. So we're going to isolate secant of x equals 5, and secant of x equals negative 3. Now to find these values, I got to take arc secant of both sides in both equations. Now if you don't have that on your calculator, you can convert this to 1 over cosecant of x equals 5, and 1 over cosine of x equals negative 3. And then you can multiply and divide, and then it's basically you're taking arc cosine of negative 1/3, arc cosine of 1/5. But I'm going to use arc secant because I'm doing this in Desmos. So here are my initial first two values, right? And they're both between 0 and 2 pi. But there's going to be two more solutions, right? So secant is positive here, and that's in quadrant 1. But secant is also positive in quadrant 4. So to get another angle in quadrant 4 with the same reference angle, I subtract this value by 2 pi. And for this one, this is between pi halves and pi. So this is in quadrant 2. Secant is negative in quadrant 2, but it's also negative in quadrant 3. So to get the similar angle in quadrant 3, I take this same angle and I subtract it from 2 pi. So rounded to 4 decimal places, these are the 4 answers. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.